So then if we understand how they gain their masses,
Mhm.
what does that exactly reveal to us about, I guess, particle physics / astrophysics, since this is happening in space, correct?
Yeah, this is happening everywhere.
Everywhere, okay.
Yeah, it's not really revealing to us that. Well, one thing that's interesting is if we do know how they generate their masses, for example, the experiment we're trying to look for this thing called neutrinoless double beta decay. So if you have this exact process, this neutron to proton conversion, and instead I have two neutrons converting to two protons plus two electrons, and I don't emit neutrinos, right?
Right.
For some reason, you can imagine that these two neutrinos are antiparticles of each other, and they annihilate within the nucleus. This is one way to imagine this occurring. If this happens, then you know that lepton number, which is one of those conservation rules, is not conserved.
Okay.
So suddenly you're in a situation where you've created more leptons than antileptons from a physical process. And so now you can imagine how this relates to like the whole like matter-antimatter symmetry problem. It's a much deeper hole to actually get there.
Right.
It's not as simple as, it's not, the matter-antimatter problem is not solved by saying these decays occur in the early universe. That's not what's happening.
Okay.
But this allows other physical processes to occur that do not conserve lepton number as well. It means it's possible. And the reason that's interesting is because there's no symmetry that's actually imposed on the standard model that tells us that lepton number needs to be conserved. It seems to be conserved as far as we can tell. So in that sense, that's why it's very interesting to me. It's like this is an accidental symmetry is what people call it.
Okay.
It's that it's not coming from some underlying kind of there's no underlying system. Yeah, there's no underlying symmetry of your system that tells you that lepton number is a conserved variable across physical processes. It just so happens so far.
Okay, and how common are these, I guess, dead ends in physics in general? If it's appropriate to call it a dead end.
What do you mean by dead end?
Well, as in you said there's no real formula to really establish this loss of conservation.
As far as I know, there isn't like a symmetry that leads to lepton number conservation.
Right.
Which is why I think it's interesting to test.
Okay.
Because, you don't have to know that certain symmetries give you conservation laws, but you know that if you have conservation laws, then you have to have some symmetry. You don't have to have, well, actually you might have to have one. But anyways, my point is we don't know what the symmetry is, so we don't end up with the conservation rule associated with it. We just seem to observe the conservation rule. And that's part of what physics is, right? A lot of it is just observing the world and seeing how it works and then saying, okay, this is how the world works. Can we explain why it works this way?
And when you say the world, do you mean on Earth or in space, or both?
Both. I mean, from the perspective that I'm talking about the world, I'm assuming that the physics is the same across the universe.
Right.
That's not necessarily something that everyone agrees with, but there's very few arguments for why it wouldn't be the same across the universe, and they're pretty on the fringes of physics today, I think. But I think it was Dirac who did actually postulate that maybe physics does change over time. For example, the fundamental constants of nature are not fixed, versus in the framework that I'm explaining to you right now, like the electron's charge, for example, is the same now and it will be the same in the future, and it has been the same in the past.
Okay.
Yeah.
Can you go more on this lack of fundamental change in nature, or the reverse, excuse me?
What do you mean?
Like the theory you just postulated.
Well, it's not, I don't really know much about it.
All
I know is that Dirac has postulated this, and there are papers written about this, and as far as I'm concerned, if there are ways to test this, then it's interesting, and if it's not testable, then it's not really physics.
That's
if
fair.
you're just playing around with mathematical models, it's like, that's cool, but that's mathematics.
Yeah, I would agree with that.
Yeah.